Okay, we're going to talk about inspection, quality control. There's a whole career set around inspection and quality control. Statistics. Statistics is used, if you've ever had that in school, for something that they call SPC, Statistical Process Control. That's used in manufacturing quite a bit. So if that's something that you enjoy, then maybe quality control is a career set for you. So this is a sophisticated device that will allow us to inspect the coolant ball that we just made on the CNC lathe. This is a digital inspection system. So we can take this coolant ball and actually place it on the stage, and it'll show us, which I have this zoomed in, the radii or the radius that we machined with the diameter on the OD and the length, the actual tolerances and dimensions that we need to hold on the part. So after you make a part in manufacturing, you have to check it. And it has to be exact, and it has to be precise, and it has to be repeatable. So there's people that get paid every day and have careers in doing nothing but, not to minimize that, but they do specifically checking parts. And when there's an inaccuracy in a part or in a process, they go back to the manufacturing people or engineers or people on the shop floor, and they actually tell them that it needs to be held to a closer tolerance. In some cases, they'll go back to engineering and they'll tell engineering that they have to re-engineer or redraw the part. So hopefully this is something that makes sense, that kind of ties in, and you can understand that in fact, once you make a part, then you actually have to check a part and you have to prove to your customer that it's accurate and that they're willing to pay for that repeatability and that accuracy.
And so what we're showing here is coming back to a known location, time over time, repetitively. So repeatability is the ability to come back to a spot accurately within a small degree of error. And in this particular case, this is showing repeatability as close to zero as we can measure in this particular case, which is down to 1/10,000th of an inch. So when you're running production in a shop, making things accurate and, more importantly, repeatable is the name of the game.
Another concept that I'd like to talk about in terms of accuracies is TIR. TIR relates to an indicator reading. And so what I have here is I have a shaft between centers. In our manual lathe component, we talked about between centers. And what you have here is as you rotate it, you'll see that this part in the indicator will move back and forth. And so if you get a shot of the indicator, you'll see that this is a 10th indicator, 1/10,000th of an inch, and it's starting at just under zero, so maybe 2/10ths on the other side of zero, and then it's going all the way to 332. So this is about a 3.5 thousandths out of round component. Now this is a heat-treated shaft. It's not ground, so 3.5 thousandths between centers is actually not too bad, considering that that's a surface that's not ground and it's just been heat treated. So that gives you an idea what TIR means. So what it means is the indicator will move backwards and forwards, and the total indication or the total reading, both plus and minus of that indicator, represents TIR. So in this particular case, this shaft between centers is just under 3.5 thousandths TIR. We'll put this 10th indicator on the lathe, and we'll go on the spindle surface, like the collet seat, and we'll expect to see anywhere from 5 to 10 to as many as 50 millionths. So obviously on a 10th indicator, that's not going to show up very well. So you need an indicator that might even show greater than 1/10th reading, maybe 50 millionths reading, maybe 10 millionths reading. It would be probably an indicator with either a bigger dial or with a whole readout on its own. We have those here around the shop. So anyway, just to review one more time, total indicator is the distance, the total distance that you go both plus and minus once again, this is a little over 3.5 thou when I reset it. 2, 2.5. So I said at a different diameter, it's about 3 thou TIR, total TIR. So that gives a little bit of an explanation of what TIR is. That has a lot to do with readings. When you set up a measurement component, these are called Joe blocks, gauge blocks. And these are ground very accurately. When you use an indicator, one of the things you usually want to do is you want to set with Joe blocks a given datum point so that the diameter of the part, however it's fixtured, is compared to a known distance. So if this part was just for example, but if you look, this 4-inch Joe block is very close to where this diameter is on this particular piece of brass in a V block. So if I wanted to measure how close or different it was, I'm right at 0 right now. And if I take this away and I bring my Joe block underneath, it's basically within a couple thousandths of 4-inch. So if this was a milled part or the length of a part or a shoulder, come to find out this 4-inch Joe block is about 2 thousandths, maybe 3, from where the top of this diameter is. So that's how you use an indicator for comparative measurement, is take a known measurement that's very accurate It's right at 0. So there's a very interesting and descriptive way to show that this top of this part on the diameter, of course it's on this Joe block, so I'd have to, or on this V block, so I'd have to take that into account, is within a couple tenths, maybe 2 or 3 tenths of a 4-inch Joe block, which is a known diameter or a known distance. And so what the indicator does, this is a dial indicator, what the dial indicator does is show you variance from a known distance. And that was a good way of demonstrating that the top of this diameter of this part is within a few tenths, 2 to 3 tenths of 4 inches from the face of this actual granite base. You also have electronic indicators, and some electronic indicators are set up so that you can actually use it to measure comparatively. If I wanted to, for example, this is a 50 millionths electronic indicator, and as I go along this part, I can actually show, if I zero it out, clamp it down, I can actually measure the straightness of the part. Okay, so this is not exactly the way I would normally do it, but there's a TIR function on this electronic indicator, and there's a much better way to fixture it than what I'm doing, so keep that in mind. But as you rotate, you can see, and you got to keep it at the same location. As you rotate the part, you'll see that the diameter will vary ever so slightly. We're in the 3 to 4 tenths range. And given the crude mechanism that I'm using for this that can at least demonstrate that you can also check TIR on an electronic indicator. In that particular case, you can see that I'm varying half a tenth right now. There's a tenth, half a tenth, a tenth. And back to 0. So that's a crude way of showing. There's also a formal TIR component in this indicator. But the case I'm trying to make is that whether it's TIR or a comparative measurement of an actual dimension, or getting an indication electronically or digitally, indicators are a good means of inspection to give you readings comparatively of where you are on your part or where you are on a fixture or a component or a machine tool. And it's very important to know that. One of the other things that let's go back and talk about thermals again. I was in a shop not that long ago that was having trouble holding a real close tolerance. A lot of my customers will hold plus or minus 1/10,000th of an inch. Well, I mentioned earlier that we live in the Midwest, and in the Midwest it gets very cold in the winter. So in shops they have large doors where machines come in and shipments go out, and these large doors expose the shop to the outside elements. So all the shops that I'm in are heated, of course, during the winter, but they're not set up quite in such a way that every time that dock door opens and closes in that sub-zero or freezing or sub-zero temperature, that air comes into the shop. And unbeknownst to the operator, he'll be running a real close tolerance job, and then he'll realize that his size all of a sudden has varied. So what happens in the big scope of things, remember in running close tolerances, everything matters. Everything matters. What happens is that cold air hits the casting, the machine, and cools the thermals of the machine tool down. Remember we talked about cast iron being very thermally stable, but it does have a warm-up period. And so when the cold air hits for any length of time, even a fairly short period of time, there may be a 2 or 3 degree temperature difference or variance, which will in essence change the location of the cutting tool or the spindle center line of where the part is. So consequently, when you're running close tolerance work, all of those facets have to come into play. Conversely, if you have a machine tool in a hot environment, and in shops they have air-conditioned shops in the South and air-conditioned shops here in the Midwest when it's really hot. You remember, the hotter things get, the more things expand. So you have thermals to contend with in that situation as well. So if you have a fan that's one of those fans that oscillates and it comes by every 45 seconds or more, something as simple as that, even though it's good for the operator, that intermittent cooling can literally play havoc on holding a close tolerance. Not that long ago, I was in the back doing a real close tolerance, and I did 10 pieces, and the 10 pieces were within 1/10,000th of an inch. And on those 10 pieces, on piece number 6, my air compressor turned on. Well, the air compressor is loud, and it vibrates quite a bit. And wouldn't you know, on piece 6, when the air compressor turned on, that there was a 1/10th difference on that number 6 piece than the first piece or the last piece. So point being is that vibration, movement, sunlight, humidity, extreme temperature up or change, up or down, or cold up or down, can all impact doing close tolerance machining.